All right, thanks everyone for being here. The joys of the first talk to an empty room. I'll be talking about the double clinching auction for wagering. This is joint work with Dave Pennock and Jen Wortman-Vaughan from Microsoft Research. So what is a wagering mechanism? Wagering mechanism is a way to elicit credible information about some future event. So each agent reports the probability of some binary event and a wager, WI, so some dollar amount that they're prepared to stake. After the event, agents receive payoffs that depend on the outcome, their own report, and the reports of other agents. So some desirable properties that we'd want our wagering mechanisms to satisfy. Weak budget balance, which says that the mechanism never loses money. Individual rationality, which says that ex-ante agents have incentive to participate. And incentive compatibility, which says that agents have a weak or strong incentive to truthfully report their probability estimate. And I should add that in this work, just like in most of the wagering mechanism literature, we're assuming immutable beliefs, which means that agents form some subjective belief about the probability of the outcome, and they don't update that belief over the course of wagering. Right, so here's an example. Will a Democrat win the 2020 election? Suppose we set up a wagering mechanism for this. Someone comes along and says, I think there's a 10% chance of this happening, and I'm willing to wager $20. Someone else, 50% chance, willing to wager $10. 70% chance, $20. 20% chance, $50. And what a wagering mechanism does is it defines a set of payments. It might look like this. So the way you read this is if we look at the red agent, if the Democrat wins, then they lose $5.70. If the Democrat does not win the election, then this red agent gains $2.70. Right, and the same for all the other agents. And these payoffs aren't just completely random. They're the payoffs defined by a wagering mechanism called the weighted score wagering mechanism. And this has lots of nice properties. In particular, it satisfies the 3 properties from the previous slide and some others. But one thing it doesn't do is it's not very efficient. And it's not very efficient in the sense that if you look at, say, the yellow player, they're willing to wager up to $50. In the worst case, they lose something like $6. The green agent, willing to wager 10, in the worst case, loses about $1. So I should add, so we're interested in this for a couple reasons. The first is that we want the idea of a wager to match our notion of a budget as the maximum acceptable worst case loss. The other is that if agents know that they can't lose their entire wager, then they might have cause to inflate their wager, and this can in turn mess with the incentive properties for reporting just their probability even. So to get at this formally, we define this property of Pareto efficiency for wagering mechanisms. We say that a mechanism is Pareto efficient if there's no profitable side bet available to the agents after running the mechanism. So intuitively, this kind of says that the mechanism is extracting all the available trade. Maybe an easier way to think about this, and an equivalent formulation, is to say that a wagering mechanism is Pareto efficient if there exists some probability, Pj, without loss of generality. This can be the probability report of some agent, such that for all agents with a higher probability belief, they lose their entire wager if the event does not happen. For all agents with a lower belief, they lose their entire wager if the event does happen. And so intuitively, we have some people maybe on a single probability report who might not be risking their entire wager, but everybody else is. So they're not able to trade anymore after we run the mechanism. So the first result in the paper is a -1. It says that it's impossible for any wagering mechanism to satisfy weak budget balance, individual rationality, weak incentive compatibility, and Pareto efficiency simultaneously. And some intuition for this in the case of just 2 agents is that if we have these 2 players, red and blue, who make different probability reports, any wagering mechanism that satisfies these properties simply defines some probability in the middle here. You can think of this as odds at which they bet against each other at. But for any choice of these odds, there will always be at least one player, here the blue player, who can move their report like this in a way that kind of pretends that these given odds are not satisfactory for them. Therefore, the mechanism has to move the odds in a way that's even more favorable for the blue player. Right? So this is a successful manipulation for them. Okay, so we can't get all 4 of these. We do still really want the first 3. So we are still going to give up on Pareto efficiency. We're just going to try and design a mechanism that comes as close to it as possible. And that's what I'm going to describe to you in the rest of this talk. And to do that, we need to think about securities. And by securities, I mean just the sort of securities that we think about in prediction markets. So we have 2 types of securities. Yes securities pay out $1 if the event occurs, and no securities pay out $1 if it doesn't. So of course, a yes-no pair of securities is always worth exactly $1, since exactly one of these securities will pay out. And this is sufficient to express the outcome of any wagering mechanism. If we have some agent like this, who's losing $5 if the Democrat wins and gaining $2 if they don't, this is exactly equivalent to them buying 7 no securities for a total price of $5. And the reason for this is that it's equivalent to giving $5 to the mechanism up front, that's the price of $5, and then getting back $7 in the case that the Democrat does not win, right, taking you from -5 to 2. So that's like owning 7 no securities. So if we have our set of payoffs from before, we can always rewrite these in terms of securities. It comes out like this. So every agent is buying either yes or no securities for some price. A couple of things to note about this. The first is that we're selling the same number of yes and no securities, 19.4 of each in this case. And this is not, strictly speaking, necessary, but all of our mechanisms will have this feature. The other thing is that if we think of these securities just as any other item, this is not an efficient allocation of these securities. And it's not efficient in the sense that if we look at, say, the yes securities, the agent that values them the most is the blue agent, since they have the highest probability that the event occurs. Yet, despite having budget left over, they're not being allocated all the securities. So another way to think about this is that the blue agent could buy securities from the green agent at a price that's mutually beneficial. So the starting point for how we want to go about this is to think about whether there's a more efficient way that we can allocate these securities. And of course there is. It's called the adaptive clinching auction. We're going to want to use this for divisible goods because we want our securities to be allocated in a divisible way. I'm going to give you some intuition about how this works in the indivisible case and carries over quite nicely. So the adaptive clinching auction is an ascending price auction for selling multiple identical items. So each buyer has a value per item, PI, and a global budget constraint, WI. And I've chosen this notation to coincide with the wagering mechanism notation because it all maps very nicely. In the wagering setup, your value per yes security is exactly PI, your probability that the event occurs. And of course 1 minus PI for a no security. And your budget constraint is simply your wager WI. So using this we can define a demand function. So the demand of agent I at price P, if price P is lower than your value per item, is simply the number of items you can buy with your budget. That's this floor of WI over P. If the price is greater than or equal to your value per item, then your demand is 0. You don't want to buy any. So the way the auction works is that as the price increases, buyer I clinches an item, and by clinch I mean that they get to buy an item at the current price, when the demand of the other agents falls below the remaining supply. This kind of should sound familiar. So the way to think about this is that we have some ascending price. Suppose we're auctioning 3 soccer balls. So as the price increases, eventually this clinching condition will bind, and someone will get to buy a soccer ball at the price. With this being bought, the remaining supply drops, so the clinching condition no longer binds. Price increases a little more until it binds again. Someone else buys a soccer ball at a higher price. Someone else might get a third one at a higher price still. So the main point of this is that every item sells potentially at a different price. This auction is actually the unique auction, which is incentive compatible, individually rational, and efficient. And as I said before, it has a natural extension to divisible goods that I won't go into, but we use all these nice properties of that auction. All right, so if we think about auctioning our 19.4 pairs of securities that we had before, according to the adaptive clinching auction, we're going to do two separate auctions, one for the yes securities, one for the no securities. We'll just run them independently, and we get this allocation here. So this is better than before, it's more efficient. The securities are going to the people who want them the most. But from the perspective of maximizing trade, we're still not doing so well. The green and the yellow agents aren't participating at all. Even the red and the blue still have budget left over. They'd be happy to trade more. So the question now becomes, can we sell more securities than 19.4? And if so, how many should we sell? So it's fairly easy to see that we can't simply fix the number of securities in advance. We can't say up front we're going to sell 100 securities, because if we do that, we don't know who or how many people will turn up. So if only one player turns up, they get all these securities for free in the auction, and we have to pay them out, so we're not going to be budget balanced. And of course, the more securities we sell means that we're going to get a lower price per security, just because of supply and demand. So some things that we thought about that are seemingly pretty natural is we could sell the exact number of securities so that the mechanism is exactly budget balanced. That's the revenue equals the number of securities. Turns out this is not incentive compatible, because even though each individual clinching auction is IC, now we're letting the agents play with the number of securities sold. So they have that extra parameter that they can play with to manipulate. Likewise, we could sell securities, the number of securities that maximizes profit. This is for the same reason not incentive compatible. But if we sell pairs of securities until the lowest price pair sells for exactly $1, this actually does turn out to be truthful. We have the same issue, but it turns out that it doesn't matter. So this is what we call the double clinching auction. I want to give you a little bit of intuition about exactly what I mean by the lowest price pair of securities. So, as I said before, we're going to sell M pairs of securities via independent yes and no adaptive clinching auctions. We'll let Cy of M denote the lowest clinching price in the yes auction, and Cn of M the lowest price in the no auction. So this is, if we think about the soccer ball example, the price that the lowest price soccer ball got bought for, right, when clinching first started. So here are the probabilities from the example before. I've left off the wages. On the top line, we have the value for the yes securities. The bottom line is the no's. That's just 1 minus the probability, 1 minus the value for yeses. Suppose we sell some small number of securities, M. If the number of securities is small, it means the price is going to be high. So let's just say that the first clinching price in the yes auction is somewhere up around 0.5, and in the no auction is somewhere up around 0.8. And the sum of these is, of course, greater than 1, which means we need to sell more securities. As we sell more, these prices each come down, they converge towards each other. Sell more, they come down some more, until finally they meet. And we know that they actually do meet because these clinching prices are actually continuous in M. So there must be some point at which they meet. And this is the number of securities that the double clinching auction sells. That's the formal definition, but you don't really need to pass that. So the double clinching auction is a valid wagering mechanism, which means that this number of securities is well defined, and it means that no agent ever loses more than their budget. If they could, then that wouldn't satisfy the properties of a wagering mechanism. And the reason for this is just because even though we're running two auctions independently, it turns out that no agent ever participates in both. So you only ever participate in at most one, and the single auction respects your budget constraint. Okay, so when we run this on our example, we sell, instead of 19.4 securities, we end up selling 30. Obviously that's better. So what does this mechanism satisfy? Well, it's weekly budget balanced, and that's because even the lowest price pair of securities by definition sells for at least $1. And every pair is only worth $1, so we're definitely at least breaking even. It's individually rational, and this follows very easily from the individual rationality of each individual auction. And the main theorem of the paper is that the double clinching auction is weakly incentive compatible. And I won't have time to give you even some intuition for that proof, but we can chat about it later if you're interested. Actually, we get a slightly stronger property that says if you have even any uncertainty about If you have any uncertainty about the reports of the other agents, then you're strictly better off just telling the truth instead of lying. So it's a little better than weak incentive compatibility. So to test how close we actually come to Pareto efficiency, because remember we do have to give that up, we don't get that, we test our mechanism on data gathered from an online prediction contest called Probability Sports, which is a contest where users predicted the outcome of close to 2,000 NFL matches. They didn't give us wages, so we randomly generated wages for them, and we ran several different mechanisms. So the ones in red are the only known incentive compatible mechanisms. We have our double clinching auction, and then there's these two here. The parimutuel consensus mechanism is Pareto efficient, but it's not incentive compatible. So it's kind of a benchmark here. This risk to budget column is taking, all the numbers are averaged across all the instances. It's taking the total risk, so that's the sum of the worst case losses across all agents, and dividing them by the total budget. So that's the sum over all agents of their wages. So the parimutuel consensus mechanism is close to 1. You know, most agents are risking most of their wager. We're a bit lower, 0.8, but still doing a lot better than the existing incentive compatible mechanisms, which are much lower. The percent full stakes is what percentage of the agents are risking their entire wager. So these are agents who definitely wouldn't have a side bet available to them. So again, we're doing not quite as well as the parimutuel consensus, but much better than the existing wagering mechanisms that are also incentive compatible. Number of securities kind of tells the same story. And also I've included the profit that the mechanism makes. And this is by no means an objective, but we do make a small profit. Okay, so I just want to close with a couple of open problems here. We have no really significant theoretical guarantees on the efficiency of the double clinching auction. So in simulations, it comes, it does a lot better than existing incentive compatible mechanisms, but we don't have any guarantees in terms of the absolute risk or the total number of securities sold or anything like that. The other one is that we don't have a way to extend this mechanism to allow for more than 2 outcomes. So it's very dependent at the moment on the structure of the yes and no securities, and it doesn't allow us to extend to 3. So if you have any thoughts on either of those, we'd be very interested in hearing from you. All right, thank you very much.